Okay, this is my first lecture of, I don't really know how many lectures there are going to be, because maybe I have to do one for the problems and one for the front, and there's 4 pages, and so there could be up to 8. But maybe there's only 4. Let's say there are 4.
4.
The first of 4 lectures for the acids and base unit. And here goes the first one, which is beginning with what acids and bases are and how they behave, and a little bit about how to do some calculations with them, with pH and all that hoo-ha. So,
that involves math.
calculations, generally, and calculators. But also we need to learn how to do logarithms in our heads.
Oh.
Yeah, I know, right?
Don't worry.
I know, I love logarithms in my heads. Okay, so you've got the definitions of acids and bases. You've got Arrhenius was the first guy, and he came up with the concept that acids are things that, when they're in solution, donate H pluses to increase the amount of H pluses in the solution, and that bases were things that donated hydroxide OH minus ions to increase the number of hydroxide ions in solution. Bam. That's sort of how most people would think of acids and bases. And it's kind of the simplest model that helps your brain be happy. So that's the Arrhenius definition of acids and bases. Going a little bit forward in history, Brunstad, Lowry, these two dudes, this guy's Danish, that's why he has a cross in his O. Hi, Brunstad. They changed the definition of bases a little bit. Acids are still donating H pluses to solution, but they encountered ammonia, NH3, and they discovered that it was a base. And this made them sad because it does not have OH minus. And so how is it a base? But what it's doing is that its NH3 can accept H plus ions from solution, which when you're pulling H pluses out, that increases the amount of OH minus that is in solution. So they changed the definition of bases from they have the OHs and donate them to, well, they just increase the amount of OHs. And, you know, sometimes that's because they're donating the OHs, but sometimes it's because they're accepting just the H pluses, and that ends up increasing the OH minus concentration. So they have a slightly refined definition of bases, these dudes. Ammonia does that, and then there are some other bases that are organic bases that start with some carbony something. It could be meth, eth, prop, any of those organic chunks with an NH2 on the end, and that's an amine. And so they're kind of related to proteins and amino acids. But this amine group, the NH2, can do the same thing that ammonia does and accept an H. And so this would become CH3NH3 plus when it accepted the H plus, whereas when ammonia does it, it starts with NH3 and becomes NH4 plus, and then that would be the acidified version. Anyway, so bam. Those are your 2 definitions. Arrhenius is kind of nice and easy in your head, but you sort of have to remember that bases can be slightly more complicated. And the good news is that the AP curriculum has dropped Lewis acids and bases.
Not fair.
I know, right?
So
we don't have to do them at all.
Oh my gosh. You guys have it so easy. You just don't even know.
There you go. So we dropped that one, and that is topic number 1. Topic number 2 is conjugate acids and conjugate bases, which is kind of thinking about acids and bases in the context of an equilibrium situation. So let's go to the black screen so I can write on it. And here's a situation where you've got this acid here, hypochlorous acid, and this amine, which is, it's a 6, it's a hexamine base thing. See the NH2? And this acid is reacting with this base. This is a weak acid, and this is a weak base. That's important to notice. That's the reason that you've got this equilibrium arrow here, because if it was a strong acid or a strong base, at least one, then the neutralization goes all the way to the right. It's a not really an equilibrium situation. But these are both weak. The organic bases are always weak bases, and we're about to get to the list of what the strong acids are, which, by the way, you have to have those memorized.
Oh, goody.
Yeah, there are 8 of them. So anyway, this is equilibrium. And here's hypochlorous acid, and here is the hypochlorite ion, and here's the hexamine something, and here's the hexammonium ion. I really should learn the name of this thing. It's not going to happen. What's happening here is, if you think about your definition, is this pen working? Yeah. This is your acid. There's your H that comes off and goes into solution as H+. And here is your base, and the reason that it's a base is because when you look at the structure, this nitrogen has got a lone pair of electrons here, which means that there's a nice happy little spot for an H+ to join in. And hey, wait, that's the definition of Lewis acids and bases. But I thought we weren't doing that. But it's fine, whatever, it'll work, it'll be fine. So anyway, so this guy is a base because he's got that little lone pair on that nitrogen, and it can suck up this hydrogen. So there's your weak base, there's your weak acid, the H+ comes off, it goes on to here. And so what you end up with is this ion, which has the ability to kind of go back and forth and be that guy some, right? So this guy is the acid. But if you had this written the other way, this guy has the ability to suck up H+. So the OCl minus, the hypochlorite ion by itself is actually a base. The base that's structurally related to this acid. So this is the acid. This is called the conjugate base. Conjugate base. Right there. And then this guy is our base because he can accept those H+, and here he is after he has accepted that H+, NH3+. So this is the base, and this is his conjugate acid. One of the skills that they will ask you to do is label these things. They'll say, this is the acid, which one is the conjugate base? It's the one that goes with the acid. And this is the base, which one is the conjugate acid? It's the guy that's related to, anyway, so there you go. That's conjugate acids and bases, and well, bam. All you got to do is label them, pretty much. So there you go. That's topic number 2. Topic number 3 is strong versus weak acids and bases. And what I was saying before is that strong things, when they neutralize, react all the way to the right. And so if you've got a strong acid or a strong base doing some sort of neutralization, you end up with an arrow that goes to the right all the way. If you've got a weak acid and a weak base, then you end up with an equilibrium set of arrows, because it can kind of shift right, it finds an equilibrium position depending on how acidic your weak acid is and how basic your weak base is. So your 8 strong acids. There's really 6 that are common, and there's 2 more that come up every now and then. So there's 8 strong acids that you have to have memorized, because what's going to happen is they're going to show you a problem with an acid in it, and if it's a strong acid, it goes all the way to the right. If it's a weak acid, you have to do all the equilibrium stuff with it. Which one do we do? Well, you have to know which one it is, and so here you go. You've got hydrochloric acid, hydrobromic acid, hydroiodic acid. So those are your halide acids here. Your hydrohalic acids, because of halogens, right? So hydro and halic, HCl, HBr, HI. These are the strong hydrohalic acids. There's hydrofluoric acid, and you would think, well, that's obviously stronger, but it's not. It's a weak acid, and I'll explain why. There's some structural reasons why things are strong versus weak acids. So there's 3 of them, the chlorine, bromine, and iodine. And then you've got several oxyacids. Nitric, which HNO3, which is from the nitrate ion. Permanganic acid, HMNO4, which is from the permanganate ion. Sulfuric, H2SO4, which is from the sulfate ion. Chromic, which is H2CrO4, which is from the chromate ion. And HClO4, which is from is perchloric acid, which is from the perchlorate ion. Notice they're all from the 8s: nitrate, permanganate, sulfate, chromate, perchlorate. And if you remember the naming system that we learned about acids last year, I don't know if I do remember. Well, you should. Where's the?
Here I am.
I don't
know if I remember.
Well, you should go and look it up in your notes from last year. Little, what are you, seahorse?
I was supposed to keep my notes.
Sure, you didn't burn them, did you?
Maybe.
Why are you on that finger?
I like it here.
Anyway, so this is nitrate, permanganate, sulfate, chromate, perchlorate. These are all of the very oxygenated ones with the most oxygens. And what's happening, the reason that these are strong acids, which first we have to remember what strong acids do, which is that they fully break apart in solution. So when all these guys are dissolved in water, 100% of the chlorines of the chlorides separate from the H pluses, 100% of the bromines separate from the H pluses, 100% of the iodines and the nitrates and the permanganates and the sulfates. Actually, we'll get back to them. These are slightly different. And the perchlorates separate from their H plus ions. With a weak acid like nitrite here, which is nitrous acid, only a small fraction of it breaks apart. So you end up with kind of a large percentage, like 95% of it, when it's dissolved in water, stays together as HNO2. That's what the definition of a weak acid is. The majority of it stays together. Whereas with a strong acid, all of it separates. So, and the reason that it separates is because the electrons have been strongly pulled away from the hydrogen. And so that H plus kind of feels free to escape because he's not really attached to the electrons because they've been pulled so far away. He's like, there's nothing keeping me here. So he leaves. And what you can see is the reason that those electrons have been strongly pulled away is because you've got so many oxygens which are highly electronegative. So you've got 3 electronegative oxygens, and so they're hogging the electrons that the hydrogens wish that they could have. And so they're like, I'll leave. So 3 oxygens, 4 oxygens, 4 oxygens, 4 oxygens, and 4 oxygens. You can see the highly oxygenated guys are strong in your oxyacids. And the same thing here. Chlorine, bromine, and iodine are also highly electronegative, so they're hogging those electrons, and so the hydrogens are like, we can leave. All right, so those are your 8 strong acids. You have to have those memorized.
Okay.
Your strong bases, these are easy. It's some metal and hydroxide. Your weak bases, in contrast, are these organic thingies and ammonia. These are the ones that are only Bronsted-Lowry bases. And are not, in fact, Arrhenius bases. So ammonia is a weak base, and methylamine here, CH3, that's what the name of it is. Ding. Methylamine is a weak base as well. Your weak acids include hydrofluoric acid, and phosphoric acid, nitrous acid, and hypochlorous acid. There are a lot more, and they come in lists, and you can tell that they're weak acids because in the list they will be listed with a number where it says Ka equals 1 times 10 to the negative. If it's got a Ka, that's a number that indicates kind of the amount that separates in the water. And the size of that number will let you know how much of it separates in the water. But they have that list for weak acids because for strong acids, all of it separates. And so you don't need the list. You don't need it to go 100% because you already know that because it's a strong acid. Hydrofluoric acid is sort of interesting. We were talking about the reason that things are strong acids and saying, well, hydrochloric acid is a strong acid because chlorine is highly electronegative. And here, stick the fish up.
But fluorine is more electronegative, so why is hydrofluoric acid a weak acid?
What's interesting about that is the reason is that the bond between hydrogen and fluorine is actually really strong. It is a strong bond. So even though the electrons are strongly pulled toward the fluorine, it takes a lot of energy to break that bond. And so that kind of overpowers the electronegativity-ness of it. So hydrofluoric is weak, phosphoric is weak. And phosphoric is neat. This is a triprotic acid. What I do? Protic is a proton, the H plus. It's got 3 of them, so it's triprotic. Sulfuric acid is diprotic. Chromic acid is diprotic, and we'll get to the funny things that those do in a couple of lectures.
Oh boy!
I know, right?
It's actually kind of interesting.
Sure it is.
Sure it is. Where's it? Why do you have him?
All right. So I think that's all of that. All right, bam. Do you have any questions?
Lots of them.
Oh dear. I don't want to hear any of them. All right, the pH scale. The pH scale, and we're going to learn about pH, pOH, hydrogen ion concentrations, hydroxide concentrations, Ka, Kb, Kw, and pKa.
Is this all on the test?
Oh yeah.
Uh-oh.
Totally. All right, so here's your pH scale. The red part is the acidic part. The blue part is the basic part. Acid is down here. Base is up here. Neutral's right in the middle. And you've got your pHs listed all the way down. So acids are acidic between 0, 1, 2, 3, 4, 5, 6, up to 6.999. 7 is neutral. The location pH 7 is exactly where the concentration of hydroxide ions is equal to the concentration of hydrogen ions. And also be aware that when hydrogen ions are mentioned, they may as well be calling them, what is that thing called? This thing, H3O+. What is the name of H3O+? Hydronium. The hydronium ion. The hydronium ion is the same thing as the hydrogen ion, because what's happening is H+, when it interacts with water, which all of these are in water, it just adds on and is H3O+. So this is really the same thing as this. Okay. So, you know, at pH 7, your H+ is equal to your OH- concentration. That's the same thing as saying this. So you can really just interchange hydronium with hydrogen ions, and it doesn't make any difference. So be aware of that. So your pH, there's acid, there's neutral where the concentrations are equal, and here's base where there is more hydroxide than there is hydrogen ions. And your pH goes from 0 to 14, which is kind of a nice, easy list. The concentrations are times 10 to the negative. So we did this before, where if you look 10, if you have a concentration of 10 molar, this side, the left side is in molar. So 10 molar hydrogen ions, that's 1 times 10 to the 0th power. And so that's, how many zeros are there? There are 0 zeros. 1 times 10 to the negative 1st power concentration is 0.1. How many decimal places is that off? That's 1 decimal place off. 1e negative 2, 0.01 is 2 decimal places off, so it's pH 2. And 1e to the negative 3 is 0.001, so that's 3 decimal places, so that's pH 3. And so you can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, on the little exponents here, if you ignore the negative, that's the pH. And what's funny is that the math for this, negative log of the pH of the H concentration, that's how you get your pH. What that is saying is, what's the exponent? Ignore the negative. So 1 times 10 to the negative 4th, the pH is 4. 1 times 10 to the negative 10th, the pH is 10. And that's if you're doing the hydrogen concentration, the hydrogen ion concentration. If you've been given, that's this one, the H+ here in the box, square brackets. And that's, let's see, we're talking, I'm going to have to run down this bulleted list and see what I've missed. If you're talking about your hydroxide ion concentration, it's actually flipped. So let me find a little spot here. So if you've got 0.1, that's 1 e to the negative 1, which is a pH of 1. If you've got 0.01, that's 1 e. This is your hydrogen ion concentration. 1e to the negative 2, and you've got a pH of 2.001, 1e to the negative 3, and you've got a pH of 3. You following me here? It keeps going up, 1, 2, 3, 4, 5, all the way up. Your OH minus, it's interesting, this thing here. Where is it? This thing, the pH and plus the pOH equals 14, where your pH is 1. This is pH. Your pOH is talking about how much hydroxide is present. Hang on. Ooh, hi. Your pOH is the opposite scale, and when you add them together, they always add up to 14. So your pOH is 13, which means that your concentration of OH minus is 1e to the negative 13, or 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1. Your pOH here would be 12, 1e to the negative 12. I'm not doing all those, but it gets one less, and this is 11, and this is 1e to the negative 11. So your pH and your pOH always equals 14. And as a result, mathematically, this there's a so no, I need a little space. So pH plus pOH always equals 14, and your H plus concentration times your OH minus concentration always equals 1e to the negative 14. And so you can see, for example, this one here, 1e to the negative 2 times 1e to the negative 12. Now here's where we start doing logarithm math in our heads. When you multiply logs, you multiply the little numbers. 1 times 1 is 1. And you add the exponents. Negative 2 plus negative 12 is negative 14. Multiply the little numbers, add the exponents. This is a formula if you're dealing with the concentrations. This is a formula if you're dealing with it already in the pH and pOH form. And to get from here to here, from the H plus to the pH, which is what I was talking about before, where you're
Hey.
Now you wouldn't think that that would have disappeared, but it did. If you're getting from the concentration to the pH, that's basically asking you, what's the exponent? The way that you do that in your calculator is negative log of n. So from the H plus to get to, there's a little square that I drew before, which is pH and pOH. To get there, they equal 14, right? To get from your H plus concentration to the pH, it's negative log of the H plus gets you to the pH. Okay. For your OH minus concentration, we just did this, which is that multiplied together, they equal 1e to the negative 14. So if you know one, you can divide to get the other. And to get from here to here, it's negative log of the OH minus concentration. Okay?
Yep.
So you can move around this square and get, for example, if they give you the pH, you can move to the pOH and then move to the OH minus. And then move to the H plus, and then move back to the pH. You can just go around in a circle if you want to. But to go this way, you have to know how to unlog, which is a particular math thing that let's go over right now. Negative log of, for example, 1e to the negative 12th. What is that?
12.
12, good. And to unlog something, there's a secret 10 here. Did you know that? Log base 10? To unlog, you go 10 to this power is this, except it's negative. So it's got to be 10 to the negative 12th is this, which it is. 10 to the negative 12th is 1e to the negative 12th. Duh, that's obvious, right? This is the same thing. But that's how you do it. So to unlog, you do 10 to the negative, okay?
Okay.
And the same way here. That's 10 to the negative, whatever it is. So we can move all around between these four numbers, and it will be necessary to know how to do that. You will be given this number and asked for all these three. You will be given this number and asked for all these three. It's a skill. You need to be able to move around this little box.
These problems are going to be long, aren't
they? They are going to be amazing. You will love them. You will love you love them. All right. So let's see. I've talked about a lot of this. Let's see what I've missed. The pH scale is 1 to 14. It can go lower because it is possible to have a concentration of strong acid higher than 10 molar. There's 18 molar. So you can actually have a negative pH. pH of like -2. That's an alarming pH. You don't want to drink that.
You don't want to drop that.
And you can also have a pH that's higher because you can have a lower concentration than 1e to the -14.
You probably don't want to drop that either.
You can have a concentration of H plus that's 1e to the -15. So yeah, it can go lower, it can go higher. You don't want to cross those very much because if you do, then you kind of die, and then you don't get to write about it. So that's why.
That's why everyone's who's written about this.
So 7 is neutral. The H plus is equal to the OH minus in that case. Down below, the small numbers are acid. It's easy to get this flipped because it just sort of naturally seems like acid would be a big number, but it's not. The acids are the small numbers in pH, and the bases are the big numbers. Your H plus concentration is the same thing as your hydronium ion concentration. And this is, I was showing you how you're using logarithms for this. A log-based scale in general means if you go up 1 unit, that's 10 times. So between pH 0 and pH 1, what you've done is you've gone from 10 molar to 1 molar. And going from 10 to 1, so going up 1 pH unit is 10 times less concentrated. So if you go up 4 pH units, that's 10, 100, 1,000, 10,000. Tomatoes are 10,000 times less acidic than pH 0. Dude. It's not just 4 times less acidic. That's the idea behind a log-based scale. You go up one thing and that's 10 times. So you got to be aware of that. So pH 2 is 10 times more acidic than pH 3. pH is negative log of the H concentration. pOH is the opposite scale. You can add those together, you get 14. Okay, the Ka. This is what we were talking about over here. So let me tell you about Ka. So the Ka, this is where this is linking acids and bases unit with the equilibrium unit from last semester. And that link is going to get stronger and stronger as we go along, so you really need to understand this.
I have to remember last semester.
Yeah, I know. It was like a month ago. Poor little brain. All right, so you have this situation.
I don't have a little brain.
Yeah, well, you kind of do. All right. You have a little brain.
What's a brain?
I know, it's so small. Oh. All right, so this is nitrous acid. What kind of acid is nitrous acid?
It's a weak acid.
That's right, it is a weak acid. And so
it's not an 8.
Yeah, it's not on the list of 8 things. So you've got an equilibrium arrow, and what this is indicating is that not all of this is separated. A small portion of it is separated. And so it's sitting at some equilibrium position of some amount of this and some amount of this in solution.
How much?
Well, that can be represented with an equilibrium expression, which the equilibrium expression, if you remember, goes kind of like this. K, and you've got your products in brackets multiplied divided by your reactants in brackets multiplied, but there's only one. So here's your equilibrium expression for this thing. This is an acid. When this is an acid and you set up this equilibrium thing, you put a little a just to remind yourself that this is dealing with something that is an acid. So your Ka is really just your equilibrium expression, and you're remembering that it's acidic. Okay. Before, we've dealt with K, or sometimes Kc, to remind ourselves that we're dealing with concentration. So this is really the same thing as all of these, like, whoop-de-doo, okay? You've done this. You're fine. The number that comes out of this will give you a good idea of how strong this weak acid is.
But it's a weak acid. It can't be strong.
But you can kind of compare the strengths of weak people, right? Like, this guy is a wimp, but this guy is a double wimp. So, a wimp would win in what do you do when you're comparing strengths? You have an arm wrestling contest. He would defeat double wimp. And so you kind of list the weak acids in terms of their strengths.
I'm a wimp.
Yeah, you don't even have arms.
That's a good point, actually.
Yeah, you would lose. Starfish would beat you. So HNO2. So you end up with a Ka. You end up with a value at 25 degrees Celsius. Remember that it's got to be at a particular temperature. They're listed for those. And actually, I should go look this up. Let me go see what the Ka is for nitrous acid. I looked in the back of my textbook, and it informs me that the Ka for nitrous acid at 25 degrees Celsius is 4e to the negative 4. And so that you would be able to compare with the Ka for, let's see, some other one, hydrocyanic acid. So for the Ka for this guy, that equals 6.2e to the negative 10. This is bigger. This is smaller because this is 0.0004. This is 0.000000062.
Oh!
So this one is larger. That means that there are more top. So there's more products. That means that this one dissociates more than that one. This weak acid, nitrous, is a stronger weak acid than hydrocyanic acid. So that's what you use these Ka4s for, Ka4s, to figure out kind of how strong they are, and also to do a bunch of math with this thing, with this number, and it'll be great. Math. All right, back to this thing. So there we go. Ka is the acid dissociation constant. Water dissociates too. Isn't that exciting? Let's talk about water. Water, to a small extent, does this. A small extent.
How small? How small?
You guys are terrible.
How small?
Well, if you're... Are you arm wrestling with your face? So, if you remember, water is a liquid here. And so in your K expression, you don't include pure liquids. And so this is the K expression for the dissociation of water. You don't include this. So all you have is the top. So your K expression for water is this, and they put a little W to remind themselves that this is the K expression for water. You would think that that would be obvious, but hey, they just like little letters apparently in this unit, so we're going to go with it. And the Kw for water at 25 degrees Celsius is 1e to the negative 14.
Wait a minute, we saw that number earlier.
Yeah, whenever things are, whenever acids and bases are messing around in solution in water, the multiplication of these two things is 1e to the negative 14. And that's something that we've already seen, and what that's talking about is the Kw. So, woo! That's where there's our little square. That's where this formula comes from. This is the water dissociation. Is there a name for that? Water dissociation constant? Something like that. I don't know. It'll be great. So there's that. Kw is 1e to the negative 14 at 25. We talked about that. And the pKa, that's a thing. We have pH, and pH uses the H, and the P stands for power or something in German, according to the internets. I don't know. Is negative log of that. So the pKa is the negative log of, you don't need brackets, of the Ka. Okay? So if you have a Ka equal to 1e to the negative 10, what is the pKa? 10. Bam. Okay? That's going to be helpful because we're going to be able to use pKa in a thing later on.
Yay, I love pKas. Why do you keep saying that we're going to be doing stuff later?
It's because we're going to be doing lots of stuff later. All right.
You didn't do Ka plus Kb.
I didn't?
Nope.
That's times.
Fine. You didn't do times.
Oh, yeah. Oh, you're right. I didn't. That one is important. When you are dealing with weak acids, and you're dealing with conjugate acids and bases, which is up here. Here is a weak acid, which is why you have the equilibrium arrow. And actually, the weak acid here, hypochlorous acid, let me look up his Ka. My textbook is over here. Hypochlorous is 3.5 E negative 8. So the Ka for that guy is 3.5 E negative 8. This is his conjugate base, the hypochlorite ion. He's a conjugate base because he is a base. Like, it's actually basic. When this is in solution, it makes the solution have a basic pH. So there's, to some extent, you know, it's a weak base. This is a weak acid. The acid has got a Ka. If you flip this thing around, like if you write the equation the other way, which you can do, because hey, why not? It's an equilibrium arrow anyway. It's just really long. That's why people don't do it. If you flip this thing around, you can find that your hypochlorite ion has got a K as well. It's got a K expression, and that's a Kb, because it's not an acid anymore.
It's a base.
And what's nice is that the Ka and the Kb are mathematically related. And the way that they are mathematically related is that Ka times Kb is equal to
14.
Kw, which is 1e to the negative 14. So if you have a Ka, you can get the Kb for the conjugate base by using this formula in a slightly different way, but it's kind of the same formula as this guy. Woo. Okay?
Yep.
Bam. Okay, yeah, that's all of them? Alright, now let's go to titrations. Do we want to go to titrations now?
Yep.
We want to go to titrations. Okay. I've shown you a titration. Not you. You. I've shown you a titration before, in which you have got some kind of beaker with some amount of acid in it, and you're like,
I don't know the concentration of this acid, alas. I wish I knew the concentration of this acid. My life would be complete if I did.
And so what you do is you go, okay, I need to know the concentration of this acid. If I neutralize it perfectly with a base that I know the concentration of, I'll be able to figure out how many moles of acid were in there. And if I know how many moles of acid were in there, I can divide that by the volume of acid that was in there, and bam, now I know the concentration. So a titration is a lab method for determining the concentration of a mysteriously concentrated acid. I know that seems like it wouldn't really come up, but it does. Titrations are things that you tend to do. When you're dripping the base, the known base, which is called standardized, because you've set it to standard, I don't know that I really like that term, but it's a standardized base, you know its concentration, into this unknown acid concentration. You drip, you drip, you drip, you drip, you drip, and you're like, hey, it changed colors, I'm done. Ding. When it changes colors, that's called the end point, and when you get there, you're supposed to end.
What do you know?
So what you've done is you put an indicator, a little chemical, this guy over here, that changes color, and you go, hey, it changed color, hooray, I'm done. If you did a good job of choosing your indicator, it will change color at the appropriate pH, and that will tell you to stop. And if you did that right, it will tell you to stop at the equivalence point, which is the point that you're interested in, the point where the amount of acid that you were wondering about is exactly equal to the amount of base that you just dripped in. And so that's the spot where you can do calculations. And so you go drip, 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 drip. Hey, I should stop. Okay, math. This is the concentration of that acid. Ta-da, I defeat lab. If you know the concentration of that base, you can determine the concentration of that acid, because the moles of the acid is going to equal the moles of the base. if you have to, for example, if you have a base that you don't know the concentration of, you can drip acid into it. It'll be great. You can do it the other way. The thing that you have to remember is that this is a neutralization reaction. As long as one of the members is strong, it will go to completion. These don't really work when you're dripping a weak acid into a weak base because it sits at some equilibrium position and you have to do, anyway. So you gotta do a strong acid or a strong base, one or the other at least, or both. But that shifts that whole reaction all the way to the right if one of them is strong. And it makes graphs. Here are the graphs. This is what the graph looks like. And they have important information and I need to tell you all about it, and it's important.
Oh.
I know, and you can do math with them. Math with graphs? Oh no.
What's math?
I know, poor. I keep calling you starfish. What are you? Seahorse.
I'm a seahorse.
Yeah. How are you supposed to do math without arms?
I use my
Head.
tail.
All right, so here is your titration graph. We've got a titration in pink here. And this pink line is what the titration graph will look like if you are titrating a strong acid with a strong base. So that pink line, it's a very nice symmetrical swoop. It starts, and these characteristics of what it looks like are important to know. A strong acid, strong base, that's the pink line, is going to be a nice symmetrical looking swoop here. It's going to start at a really low pH because it's a strong acid. And it's going to slowly increase with a nice kind of regular slope until, bam, it jumps up like crazy. And so what you're doing here, if you look across the x-axis, is you're dripping 10 mils in, 20 mils in, 30 mils in.
What?
You're dipping the base into the beaker of acid. So you're dripping base, you're dripping base, you're dripping base, and bam, as soon as you drip in 40 milliliters, this thing went insane. It went from pH like 2.5 to pH 10.5 in the space of one drip. Goodness, that's alarming. It changed colors at this point. Because your indicator changes colors at, say, pH 7, and that happened. So it hit that pH, it changed colors, and you went, oh, I'll stop. And so that told you that at 40 milliliters of base, you have reached your equivalence point, which means that 40 milliliters of base contained precisely the amount of base needed to neutralize your acid.
Strong acid.
Yeah, your strong acid, because the pink line is the strong acid and the black line is the weak acid. This is two different titrations on one graph to save space, sorry. So what you end up doing is you go, okay, well, 40 milliliters of base at 0.15 molar base is this many moles of base. Well, that's how many moles of acid there were. And that's how many moles of acid there were, and there were 50 milliliters of acid, so moles divided by liters is, and so you can figure out the concentration by doing that. And a characteristic of a strong acid, strong base is you've got a really tall jump from 2.5 to 10.5, so like a big pH jump. And then after that, it kind of levels off and stays at about the same pH for a long time. Okay?
So what's my equivalence point?
Your equivalence point is the point right at 40 milliliters here. Right at 40 milliliters, that's your equivalence point, and the pH in the middle of that jump is the pH at the equivalence point. So that's here on the pink line, and that's pH 7, which is important because a strong base and a strong acid titration is gonna have an equivalence point at pH 7. Weak acids and weak bases mess up your equivalence point. It's not at pH 7 anymore. But right at 40 milliliters, it's pH 7. And right after it, it's not anymore. All right, so that's your strong acid, strong base titration.
So what is my definition of an equivalence point?
Your equivalence point is when the amount of base dripped in equals the amount of acid dripped in. That is the point. That is the equivalence point. The end point is important when you're actually doing it in the lab, because your eyes cannot tell you, oh, the concentrations have suddenly become equal. You can't do that. You can't see that. What you can see is, hey, it turned pink. That's when you stop. And you set it up so that it will turn pink. at the equivalence point, unless you're dumb and you got the wrong indicator.
I'm not dumb.
Yeah.
I don't think she believes me.
Yeah, poor little starfish. Dang it. I'm dumb. Okay,
Yes.
so a weak acid titration looks different on a graph. And you need to be able to look at a graph and go, hey, that's a weak acid titration. And these are the things that you would look for. They have a funny little bump here at the beginning. It goes whoop. This one is and this one goes whoop. Okay? There's a little quick increase at the beginning. It starts higher up. Down here with a strong acid, the pH, you start at like 1 or 0 or something like really low. With a weak acid, you're starting at like 3 or 4, something like that. It's not as acidic. It's weak. So you start at 3 or 4, and then you go along, and the change is more gradual. And you have a nice region here where the pH is changing nice and slowly. And your jump is not as high. So your jump with a strong acid, strong base titration is like something like 7 or 8 points. With a weak acid, strong base titration, you've got a jump of, let's see, from 6 to about 12, that's like 6, and this is from 2 to 12, that's like 10. So you can see it's a shorter jump. And like right here, the black line joins the pink line here because the end of it is the same. But the beginning is different. So you got the equivalence point kind of right in the middle of this jump, which is about here. And so the pH at the equivalence point for a weak acid titration is higher. It's not pH 7. It's more like, in this case, 9-ish. Okay? It's more basic when it is at the equivalence point than a strong. And the other thing that's really cool, and this is important because it's an easy multiple choice question, is that in a weak acid titration, there's a thing called the half equivalence point, which is an important point. And so here's how you figure out what the half equivalence point is. The equivalence point is at 40 milliliters. What's half of that?
20.
20. At 20 milliliters, that's your half equivalence point. So right there, that's a spot that is important on a weak acid titration. It doesn't really matter on a strong acid titration. Because what's cool about the half equivalence point of a weak acid is that at that spot, the pH is equal to the pKa.
Ooh.
That's important because if you don't know what weak acid you have, you can do a titration of a mysterious acid. You don't know its concentration. You don't know what the acid is. You can get to the equivalence point. You can divide that by 2, and you can figure out what the Ka is. And then you can look it up in your table and find out what acid it was. So this spot, the 20 milliliter spot, which is half of 40 milliliters in this one, you go, okay, well, the pH is 5. That means my pKa is 5. What is the Ka?
It's the negative log thing.
It is the negative log. So if you've got a 5, what was the concentration that it came from?
10 to the negative 5.
Yeah, so your Ka in this one is 1e negative 5. Okay?
Okay.
That's kind of cool. So that's something else. That's an important dude. I think that's everything for this, except we can actually calculate the concentration of our acid. So let's do that.
I love doing things.
Oh, yeah, me too. I think I'm going to stop after this box because it's getting long. All right. Do I have this written down somewhere? Yeah. I'll look at my paper. Let's find some black space. Good heavens. All right. So what we have is 40 milliliters of acid, and we don't know the molarity. What was our equivalence point? We had our base.
40
40
milliliters.
Wait. not 40. No. 50 milliliters of acid. Sorry, I changed it on the
Okay,
notes
that
on here.
makes more
Yeah, it
sense.
says
Okay, there we go.
it says 50 here.
Okay.
Yeah, I printed out a different one for us to look at. So that's 50. It's 50.
Okay.
50 milliliters of acid, and 40 milliliters of base
Is the equivalent.
is the equivalence point.
That's how much it took to neutralize the acid?
That's how much it took to neutralize the acid. And what that means is the mole, at the equivalence point, the moles of base is equal to the moles of acid. Because what we're doing is we're doing this reaction, H, and we don't know what acid it is yet, so we're just going to call it HA. Okay, HA plus NaOH. What are you going to make when that neutralizes?
H2O plus NaA.
Yeah, whatever this is, it might be Cl or something. This is a 1 to 1 to 1 to 1 ratio. It would be different if you had a diprotic acid, but we're not messing with that yet. Yeah, we'll do that later. But your moles of base are equal to your moles of acid. Your moles of H's and your moles of OH's, they end up being equal because you make an H2O. So what we need to figure out is our moles of base. We have 40 milliliters of NaOH, and that's 40 mils of sodium hydroxide solution over 1. Milliliters of sodium hydroxide solution. And that's 1,000 milliliters of sodium hydroxide solution. We know the concentration of this because it is listed here. How many moles are in 1,000 milliliters?
0.15.
Yeah, 0.15 moles of sodium hydroxide are in 1,000 milliliters of sodium hydroxide solution. And what that's going to give us is, I don't know, whatever, 40 times 0.15 divided by 1,000. So that's 0.006 moles of sodium hydroxide. That's how many moles of sodium hydroxide we dripped in.
Okay.
When we dripped that in, there was no more acid left.
Okay.
That means that there were 0.006 moles of acid in our sample that we titrated. What was the concentration of the acid?
0.006 moles divided by 50 mLs of acid, because that's what we started with.
0.006 moles divided by 50 mLs. It's got to be in liters. Yeah, so 0.05 liters, because 50 is 1, 2, 3 liters. And what that gives you is 0.12 molar acid. Bam. Okay?
Okay.
That's how you do these. And I'm going to stop now because this one's getting long. Thanks, folks.